In this podcast, we're going to talk a little bit more in depth about metallic bonding and what it actually entails. All right, first off, let's talk about metals. We just have a lattice of positive ions when they all combine to metallically bond, and then we just get a sea of electrons. So the electrons really don't belong to any one atom. And this works because metal atoms have very low electronegativity, meaning they don't have a lot of want for electrons. They are completely okay giving them away. Right. Basically, you have metal cores surrounded by a sea of mobile valence electrons. So the valence electrons are moving throughout, as you saw in this picture right here. They're moving all over the place. And then you have the positive ions, the metal, the nucleus of the metal, and its inner shell of electrons, all fixed in a fixed position. The atoms are considered to be delocalized, meaning they aren't associated with any individual atom, and this is what gives us all the cool properties that metals have. All right, some examples of metal: lead, silver, gold, copper, zinc, iron, and then we have alloys, which are combinations of metals, like brass is a combination of copper and zinc, bronze is a combination of copper and tin, and stainless steel is a combination of iron, chromium, and carbon. All right, don't forget that the majority of the periodic table is metals, as indicated by the blue here. So we see a lot of metallic bonding. There are several properties of metals that make them useful. They're good conductors of heat and electricity, so we can use them for cooking, electricity, things like that. They're shiny and lustrous, so we tend to like to use them in jewelry. They can be pounded into thin sheets, which is what we term malleable, or they can be drawn into wires, which is what we call ductile. Metals do not hold on to their valence electrons very well because they have a low electronegativity, which is going to give them all of these special properties we just discussed. So why do metals conduct electricity? Well, electricity involves the movement of electrons. Therefore, metals are good choices because they have free electrons that can move, allowing the movement of other free electrons, such as electricity, through it. Which one is going to conduct electricity better, sodium, magnesium, or aluminum? Well, let's think about this. Let's think about the valence electrons, the delocalized electrons that each would have. Sodium could only contribute 1, whereas magnesium could contribute 2 delocalized electrons, and aluminum could contribute 3. So aluminum is actually going to be our best choice here for conducting electricity because it has more delocalized electrons. So the higher the charge, the more delocalized electrons, the more the metal conducts. Remember, nonmetals do not conduct electricity because they gain extra electrons. And usually metalloids conduct very poorly except at high temperatures where their electrons become more free to move. All right, another trend is malleability, which is the ability to bend or hammer into a sheet. Metals can do this because their electrons are delocalized, which means they don't belong to any specific atom. So when you bend the substance, the electrons can move around, allowing the substance to be changed in shape and formed into a thin sheet. Ionic compounds, you could not do this because when you try to shift them around, you're going to get positive ions beside another positive ion and a negative beside a negative, and that's going to cause repulsion. Well, with metals, because those electrons move around, it allows us to bend and pull and do all we want with it, and those electrons just kind of go with whatever you're doing to the substance. They can move around as well. Malleability decreases across a period, so smaller atomic radiuses tend to give off more electrons, and it increases going down a group. So larger atomic radiuses and a weaker attraction to those electrons that are on the outside. So they're going to more easily give up those outside electrons when they have a lot of electrons completely. All right, ductility is the ability of a substance to be stretched into a wire. Metals are very ductile for the same reasons as malleability. When we stretch and move the atoms around to change the shape, the electrons are able to move freely, which decreases the repulsion and allows us to split the structure and stretch it into a long wire. Ionic crystals, again, you can't do this because when you shift them, the charges line up and it causes split in the structure and the inability to stretch or hammer it into a different shape. All right. Metals also have low volatility. Volatility is the tendency of a substance to vaporize, leave the solid liquid state, and become a gas. And they're going to have this because they have intermolecular forces and the structure of the substance with the delocalized electrons. They're all interacting with one another. So they have little reason to let go of those attractions and become a gas, a vapor. So the interactions between all those delocalized electrons and those positive cores are what cause them to have low volatility and therefore not escape to vapor phase very easily. When you're talking about valence electrons, just remember the shell model, because the shell model helps us understand that the more valence electrons we have, the more delocalized electrons we'll have in a metal, and the more of these properties we will see. Metallic solids often are pure substances such as, copper, gold, iron, but we also can make mixtures of them, and these are called alloys. So brass, bronze, and stainless steel are all examples of alloys that have different combinations of metals in them. And we can understand the properties of these alloys if we understand the size of the atoms that are in the alloy. So we have an interstitial alloy, which is when we have atoms of different radiuses where these smaller atoms can actually fit in the spaces between the bigger atoms. Steel is a really good example of this because carbon is very small and it can fit in between the iron. And because the atoms do not expand the lattice that the metal makes, the density is often increased very much. So we don't get any more space, but we do get a lot more stuff in that space, a lot more atoms in that space. These atoms are going to make the lattice more rigid, less able to slide past one another, and therefore they're going to decrease the malleability and ductility. So interstitial alloys are going to have lower malleability and ductility than you would see in just the metals themselves. The second type of alloy is going to be a substitutional alloy, where we have atoms with similar radiuses, and we're going to substitute one for another in the lattice. Brass is a great example, where we substitute copper atoms for zinc atoms or such. The density usually does not change very much. It's going to end up being very similar to the component metals that are in it. And therefore, the alloy is going to remain malleable and ductile because all those electrons are still free to move around. All we did is replace one for another. We have nobody occupying the space and making the structure more rigid. Alloys are still going to have that sea of mobile electrons, and they're still going to conduct, therefore. Here is a good example. So here we have a pure metal. We have a substitutional alloy where we just take out some of the red dots and put in blue dots. And then we have our interstitial alloy where we have all the red dots still there and we just add some little green ones in between. Those are metal atoms such as carbon that could fit in between iron and like steel. And then we have a hybrid. We have a substitutional / interstitial alloy where we have some substitution involved and then we have some that are fit in between the spaces. And that pretty much brings us to the last point where sometimes we can form alloys that are going to alter the chemistry of the surface of the substance. So here's an example of a chemically inert oxide layer in stainless steel. So stainless steel has the iron which reacts with oxygen. And we're going to add a chromium layer that is going to protect the steel layer below from being oxidized, being changed, or reacting with the air. You see if you get a cut in it that it actually reforms itself. So this is a really nifty thing that they've started doing with a lot of our steels to help them last longer. And that's all there is to metallic bonding.